Alright, welcome back ladies and gentlemen. We're on 12.2 day 1, techniques for evaluating limits. Okay, we're going to be evaluating limits algebraically when direct substitution fails, and then find limits involving difference quotients. Alright, now, basically if I'm trying to find a limit and I can't just plug in, basically what that means is you end up with some kind of an undefined thing. In general, the easiest way to be undefined is to have a zero denominator. So, right here is our first one. If I have the limit as x approaches negative 5 of x to the third plus 125 over 4x plus 20, well, hopefully it's pretty obvious that if I plug a negative 5 here into my denominator, I'm going to end up with negative 20 plus 20 and have a zero denominator, which of course is undefined. So basically what we're going to be doing here is trying to eliminate the thing that gives us the 0 in the denominator. Okay, and sometimes by canceling, we'll be able to do that. Alright, so basically right here, I still have my limit as x approaches negative 5, but alright, now I've got a numerator and denominator that are both factorable. Okay, the x cubed plus 125 is a difference of cubes. The cube root of x cubed is x, and the cube root of 125 is 5. And then, of course, get a trinomial out of this, and square the first guy, x squared. Remember the opposite sign of what you used first. And then you take the product of the two, so in this case 5x. And then finally you take the second guy squared, and it's always positive, to get a 25. Alright, from there, we factor the denominator, a little bit simpler factoring here. You add a common 4 to pull out, and that gives you an x plus 5. Okay, and now what we can do is cancel the x plus 5s, which again was basically the thing that was giving us a zero denominator, so we're now dealing with limit as x approaches negative 5 of kind of our leftovers here, x squared minus 5x plus 25 all over the 4. And then from there, now if I plug in my negative 5, I don't get a zero denominator. So really what I can do here is simply plug in the negative 5, get negative 5 squared, etc., minus 5 times negative 5, plus 25, all over that nice pretty 4 on the bottom. And then working horizontally, I've got a 25 and another 25. It's going to be a 50. 50 plus 25 is pretty much going to be a 75. And then we got that over a 4. So 75 fourths would be the limit of that particular expression. Alrighty, another useful thing you can do to avoid an undefined value in your expression is to rationalize. Now, admittedly, rationalizing is normally something we do to denominators, but a nice calculus trick, depending on the situation, is to rationalize a numerator. And actually, if you notice, right now, if I plug in a 0, I have a 0 denominator, but I've got this icky root-looking thing in a numerator, and by doing a little bit of manipulation, I can actually come up with something a little nicer for the thing that I'm trying to do. Alright, that being said, of course, if I'm going to rationalize, I have to multiply by the conjugate. In a situation like this with a kind of binomial sort of thing with two different pieces. Okay, the first piece is the x plus 9, and then the other piece, again, I'll have to change the sign, so this becomes a plus 3. So now I'm going to use an x plus 9 plus 3 on the denominator as well, and basically multiply this out. Okay, of course this is a little messy looking, but, you know, hey, welcome to high-level math. Alright, I'm going to FOIL the numerator, but remember, I'm foiling conjugates, so if you remember conjufoil, I really only have to do the f and the l part because the o and the I are going to cancel. So here we go. The root x plus 9 times the root x plus 9 gives me a nice clean regular x plus 9. And again, the plus 3 times the root and the minus 3 times the root will cancel, so I'm not going to waste my time. And then I've got a negative 3 times a positive 3, which gives me a negative 9. Alright, now I admit I'm going to cheat a little bit because I know what to expect. I'm not going to distribute this x into the other half of my expression. I'm just going to leave it as x parentheses root x plus 9, and then the plus 3. Now admittedly, if you distributed them, that'd be fine, and in just a few seconds you'd end up having to factor it back out, so you can do some canceling, because notice up here on the top I have a plus 9 and a minus 9 that will cancel each other out very nicely, and I'll be able to cancel the x with the x that's down there. Just for the sake of showing nice work, I'm not going to do that yet, but here it is. X on top, x on the bottom, that will shortly disappear, and then the x plus 9 plus 3 hanging loose. So here we go, nice fancy red canceling color. Alright, so one more step, gives me the limit as x approaches 0 of a 1 over a root x plus 9 plus 3. Okay, now at this point, if I think about what that 0 is going to do for me, it's not going to create a 0 in the denominator, so I'm free to plug it in and see what happens. Alright, so plugging in the 0 for x, let's see, 0 plus 9, checking my calculator, quickly gives me a 9, and then if you allow me to do so, square root of 9 is 3, so this is really just 1 over 3 plus 3, and I'm pretty sure that works out to be 1 over 6. So there you go, the limit of that whole nasty looking thing as x approaches 0 is 1/6. Now, limits involving trigonometry is a little bit tricky sometimes because there are some values that are undefined which aren't maybe obvious at first. But, for instance, right here, I get the limit as x approaches 0 of cosecant over cotangent. Well, cosecant is actually undefined at 0, as is cotangent. So right now, if I plug in a 0, I get undefined over undefined, which really doesn't make a whole lot of sense. But again, trigonometry is a very, very nice thing, at least for the functions, because they're all replaceable by other things. So, depending on their situation, sometimes you can rewrite this in a much nicer situation for what you're trying to do. For example, cosecant, of course, could be 1 over sine, and then cotangent is cosine over sine. And granted, we've made a complex fraction for ourselves right now, but the good news is that complex fraction is going to actually make our job easier here, because now I'm going to have 1 over sine times, again, I'm flipping this guy over, so now I have sine over cosine. And again, doing a little bit of cleanup. And switching to my fancy red canceling color. We can cancel those two guys out, and I'm left with a limit of 1 over cosine. Okay, now realistically at this point we could turn this into secant, but I think most people probably think better in terms of sines, cosines, and tangents, so I'm going to leave that as cosine, although again, if you're more interested in doing so, feel free to turn that into secant. But at this point, again, I'm going to go horizontally as my kind of, hey, I'm plugging things in sort of signal. I'll plug the 0 into here, and if I have 1 over cosine of 0, well, if you remember, cosine of 0 is equal to 1, so this thing actually has a limit of 1. Alright, then there's complex fractions, which have their own little interesting little twist, because right now I'm doing the limit as x approaches 0, which hopefully is pretty clear that I'll have a 0 in this denominator here, but you'd also have to have a problem if I had the limit as x approaches -5. And you might think, well, that's no problem here, but if you look, because remember, sometimes our numerators have denominators in them, and so you have to watch out for values like that. Okay, well, moving on to the situation we actually have right here. Alright, the good news is complex fractions, by their very nature, are things we want to kind of simplify. So, a few things right here. I'm going to make that plus -1 to avoid any sign mistakes I might make later. Okay, and again, I want to compress my numerator into a single fraction, and maybe even think of my denominator as a fraction itself. That might help things sometimes. But, again, find a common denominator on top. I've got an x plus 5, and on the left side of my numerator, I'm going to need a 5. Alright, and just in my head, it makes more sense to go horizontally with these things. Feel free to go vertically if you prefer. But whatever the case, I'm still talking about the limit as x approaches 0, but now we've got a 5 on the kind of upper left part with the 5x minus 5, or sorry, x plus 5 actually. And then I've got plus, and again, because I like to change that, so I'm looking at a negative x minus 5 on my right side numerator. And of course, the whole point of doing what I just did was to have a common denominator, so no shock, I've got 5 and then x plus 5 all over my denominator. And you know what, let's factor that right now because we're probably going to need to anyway later, so we might as well take care of that while we've got it. Alright, at this point I kind of ran out of room horizontally, so I'm just going to kind of bring this down to the left and take my numerators, put them together, and I do have a positive 5 and a negative 5 that'll cancel. So now my limit as x approaches 0, okay, my numerator of my numerator works out to be a negative x, and then my denominator of the numerator is still the common 5x plus 5 that we had a second ago. And then my big fraction bar gives me that thing that we just factored, x plus 1 all over 1. So again, working horizontally. Okay, I'll keep my numerator and flip my denominator over. So now I've got a negative x over 5x plus 5. I know this does get a little redundant here, so if you can skip a step or two as you're doing this. I am more than happy to have you do that. So now the 1 flips up to the top, I've got an x, and then the x plus 1 in the bottom. Alright, now I'm in a situation where my x cancels with my other x, and again, since I've reached the edge of this, I'm going to switch over here to the left and get my limit as x approaches 0. Okay, my top, we have a negative sign with a 1, so just a negative 1 right there. And the denominator, we do have kind of a messy sort of thing. 5, that's a 0 right there, believe it or not. X plus 5, and then x plus 1. Okay, now again, the whole point of doing this is now I've created a situation where I plug a 0 in, and I no longer get a 0 in the denominator. So I'll do that at this point. I have a negative 1, plugging in a 0 for everything. I basically have a 5 there. I have another 5 is kind of like my middle chunk. And plugging in a 0 here gives me a 1. So this becomes a negative 1 over 25. And there you go. And now calculus is a big fan of these different quotients. As we get further into calculus, you will see this thing a whole lot, this f of x plus h minus f of x over h, which we did a lot earlier in the year, but we never had this little limit notation right next to it, but it's actually very important for calculus. But anyway, here we go. Okay, well, of course, if I want the limit of h approaches 0, and I've got an h on the bottom, well, pretty quickly that's something that's undefined. So hopefully, by doing my f of x plus h minus f of x, I can accomplish some sort of way to eliminate that h. And there's no real way to know for sure, unless you know already in advance what you're doing, so let's get into it. Alright, so again, first thing first, f of x is this guy. And if I want f of x plus h, again, remember all I'm doing is replacing the x with the x plus h. So kind of as I get going here, let me get my limit down. Alright, now again, f of x plus h. So f of x is this. So I write my 3, and then I see an x, so instead I put in x plus h. Squared plus 7. Now I'm going to subtract the f of x. Okay, good idea, I think. Put that in parentheses, helps sort out any sign errors that sometimes get made. Alright, and that's living on top of an h. So again, at this point still, plugging in h, bad things happen, so I got to keep simplifying this thing down to see if I can get something better. So limit as h approaches 0. Okay, and I'm going to FOIL out the x plus h, and if you don't mind, I'm going to distribute the 3 at the same time. Of course, the x plus h squared, if you need to see this, is x squared plus 2xh plus h squared. And again, just to save a little time here, I'm going to distribute the 3 in there as well. So I'm going to get a 3x squared plus 6xh plus 2h squared. And then I've still got the plus 7, and now distributing my negative sign gives me a negative 3x squared and a negative 7. Again, all sitting on top of an h. Now the good news is that I have a negative 3x squared and a positive 3x squared. I also have a positive 7 and a negative 7, so a whole lot of stuff just canceled. Okay, and at this point, I've got the limit as h approaches 0 of 6xh plus 2h squared all over h. And then the good news is that at this point, I've got something that can factor an h out, or if you prefer, I can simply eliminate an h out of all 3 terms. So at this point, I'm looking at the limit as h approaches 0 of canceling out an h, a pretty nice 6x plus 2h. Alright, now I'm getting a little bit low on space here, but I think I can pull this off horizontally. This equals, plugging in a 0 now for h, equals 6x plus 2 times 0, which I don't think I need a calculator to tell me that that's going to be just a plain old 6x. Alright, if you print out the notes yourself, I left an entire page for this problem, just in case you have a little bit bigger handwriting as me. Hopefully you didn't have any trouble getting all that in on the page. Alright, I'd like to do another one of those because, quite honestly, that first one being a simple polynomial came up pretty cleanly. This one being a rational function, or a fraction, if you will. This one's going to be a little messier, and just kind of want to demonstrate how you're going to have to handle that. Alright, so first thing first again, I'm trying to take the limit as h approaches 0, and I've got an h on the bottom, so it's going to be definitely something we're going to need to clean up. So, limit as h approaches 0. Okay, again, f of x is this guy, so if I'm doing x plus h, he becomes 6 over, there's an x, so I put x plus h instead, and I've still got the minus 3. Alright, now again, this is part of my numerator, which is going to get a little messy, but here it is. Now minus the original f of x, which is 6 over x minus 3. and that's living on top of an h. Okay, again, one of those things, since I'm subtracting, now granted I don't really need parentheses here so much, but since I am subtracting, I do want to turn that to plus a negative 6, because that's going to help show what's going on in just a minute. Alright, that being said, I have two different denominators that I can't multiply anything by one to turn it into the other, so basically I'm stuck multiplying them by each other. So the right side here needs an x plus h minus 3, top and bottom. And then of course the left side, I'm going to have to kind of squeeze this in on a diagonal here, needs an x minus 3, top and bottom. Alright, so got to try to clean this thing up and see if it gives us something a little nicer to work with, and hint, it does, but let's see exactly what it gives us. Limit as h approaches 0. I can distribute here, giving me a 6x minus 18, and that's living on top of something again that I'm not going to multiply out, at least yet. So x plus 3, x plus h minus 3, and I've got plus, and I distribute my negative 6, brace yourself, negative 6x minus 6h, and then a plus 18, all over that same messy looking thing, x minus 3, x plus h minus 3. And again, living all on top of that h. Don't forget about this guy. Alright, at this point, I'm getting a little thin on room, but here we go. Limit as h approaches 0. Okay, now the good news is, I have common denominators here in my numerator, so I can combine my numerators in the numerator. Sounds a little crazy, but there it is. So the 6x's cancel, and I've got an 18 that cancels the other 18, because a positive versus a negative. So I actually, pretty quickly, have something that's going to clean itself up fairly nicely. Okay, now the numerator of my numerator is simply a negative 6h, and the denominator of my numerator is x minus 3, x plus h minus 3, and again, still living on top of that h. Okay, now for what I'm about to do, I'm going to write that as an h over 1, although I did about run out of room here, so I'm going to take this to the next slide. Alright, so picking up where we just left off, I've got this, I just simply copied from what I just had, so don't need to rewrite that. Okay, but I'm going to start cleaning it up. So, limit as h approaches 0. Okay, now this previous step I still had an h. It is in the numerator, but it's the numerator of the denominator, so it would make a 0 in the denominator ultimately, so I couldn't plug in yet. However, now that I have something that I can turn into a division problem, I have negative 6h over our icky denominator of the numerator. Imagine saying all that stuff 5 times fast. Alright, times, okay, now again, just simply flipping that over gives me a 1 over h, and now magically my h's will cancel out, and I will be left with something that is much, much nicer to play with. So a limit as h approaches 0 of a negative 6 on top of, and I know this doesn't look very pretty, but I've got x minus 3, and then x plus h minus 3. But notice now, if I plug in a 0, I don't create a 0 in the denominator, so I'll do that. So I get my negative 6 on top, and again, by putting a 0 right there, it actually creates a very interesting situation. I've got x minus 3, and then again, with him gone, I have x minus 3 again. So if you'd like to write this in a sort of compact way, it's actually x minus 3 quantity squared. So there's your differential quotient based on that icky fractional function, and there you go. Okay, hopefully that made a little sense, and well, of course, as always, ask me any questions you have. I want to see you in class. See you then.